Now, it's just taking a minute to load the question. Oh, here we are. Super. Oh, do you mind getting that side? Thanks. Sorted, Dorian?
Sorted, kind of, yes. He wanted me to go down so I can give it to him. And I know, I mean,
Yeah. I was asking Zach who you bought this from.
Harvey Norman.
Yeah, okay. They're a bit of a...
No, the Harvey Norman girl was fine.
Was it? It's just the delivery people.
The really bad.
And who's the delivery people?
No idea. I've
Just
had 3 deliveries so far, and this was the worst one.
Well, Harvey Norman needs to do a better job of who they pick for the delivery, you know? Okay. So like I said, we'll take turns here. Give one similarity. Sorry, is this?
Yeah, it's the right one.
It is, yeah. Oh, why did I put it into this section? Because it talks about being polarized.
We did kind
You did?
Yeah. No, I was just wondering why I put it here and not in the electromagnetic lesson. And it's because it mentions polarization. Yeah. There's polarization we did in the second lesson.
Okay.
Yeah. What's one so I don't think I need to write this down. What's one similarity and one difference between infrared and ultraviolet? Okay, so what's one similarity? What's one thing they both have in common?
Yeah, on the same spectrum.
Oh no, that's too broad. A bit more precise.
No medium of propagation.
No medium of propagation, yeah. Or they both travel with speed c in a vacuum.
Yeah.
Or they're both transverse. Yeah. I can't really say they're both electromagnetic because that's already given in the question.
Yeah.
It would be like saying they're both waves, you know. But what's the difference? Well, what's the only difference between the two? There's only one difference between them: the frequency. And who has the higher frequency?
Ultraviolet.
Yeah, UV. Fair enough? Yeah. Okay, so for 1 mark, what does it mean to polarize a wave? Now use your best English, the shortest sentence you can make to describe polarizing a wave.
To convert incoming electromagnetic waves so that they only travel on one plane.
Yeah, so many of those words can be replaced by one verb.
Eliminate.
Not that verb.
Convert.
No, she already used convert. There's another verb she can use that can delete a lot of words in that sentence.
Restrict.
Getting closer.
Limit.
Restrict is okay and limit's okay. Confine.
Confine.
So you could say polarization, to polarize a wave means to confine its vibrations to one plane. That's the shortest sentence I can think of to describe it. To confine its vibrations to one plane. Now, Zach, you said the verb you said is fine too, restrict. And Dorian, I think you said limit. This is also fine. Okay. Are we okay with question 1 there? Now I'm going to do number 2. It's a calculation question. Infrared wavelength of 850 is transmitted down a fibre optic cable and has a refractive index of 1.58. What is the critical angle for light at the boundary between the cable and the air? Now they don't say this in the question, but you can assume that the critical angle for air, the refractive index for air is the same as the refractive index for a vacuum, meaning 1. And the index for, what the heck is it?
Optic fiber cable.
FOC, is 1.58. And the formula I gave for critical angle is sine inverse 1 over 1.58. So do you mind bashing that in, somebody?
Degrees or radians?
Degrees.
39.
39.23.
Easy peasy so far, right? The cable is then surrounded by a material of refractive index 1.48. Determine the critical angle now. Okay, now, I think I've discussed this before in class, that sometimes the author of the exam has little imagination and asks you to do the same thing again with different numbers, which is really what's happened here. So C equals sine inverse.
1.48.
Yeah. Such a waste of life.
69.5. Nice. That's a nice angle.
Okay, Zach, calm yourself down now there. All right. Easy peasy. That's actually, I had the answer uploaded for this already.
Nice.
39.3.
Yeah.
Whoa!
I
I thought you told me 0.2.
I said 2.5 and then I said 3.
Okay. Oh, the 3 was replacing the
Three was
2.5.
replacing
Yeah,
the
thank
2.5.
you. Okay. How many marks? 2 and 1 is 3. Yeah, okay. Right, sorry, do you need to write this down?
Yeah.
Yeah, you got that? What did you have a passion for food?
Lamb kebab.
Oh yeah, I've had that before, that's good. What do you have, Zach?
Mixed, so chicken and lamb.
Who else was there? What do you have?
No,
Lamb.
The lamb?
Lamb with rice.
Lamb and rice, yeah. Do they give you student prices or not?
There's student prices?
Well, I'm asking you, do passion? No.
No, I don't think so.
Well,
Oh,
today
I almost,
he had
I
like
almost
a-
got hustled.
Yeah.
Well, you almost got hustled.
He had a problem with his car or something.
They can't
He was
issue
like,
it.
oh, 40 for the total, and it was less.
So it's €9 each.
You had trouble with multiplication, was it?
Yeah, so he was like, he's like, don't worry, I'll charge you €10
Only
per
10
person.
euros for everything.
I think I know the guy you're talking about. He's a bit of a jokester.
He's from
Uzbekistan.
Uzbekistan or Kyrgyzstan or something.
Kyrgyzstan.
Kurdistan.
Cheery fella.
Kind of.
Happy kind of.
Yeah.
Yeah, I know him. Yeah, no, I think he was only winding you up. It wasn't serious.
Yeah.
Don't worry. Okay. 3 now. Okay, I think you can do this one in like 1 minute. So let's have a go at that. Give this one a go here. Number 3. Oops, there you go.
Transparent materials.
Well, the word transparent is redundant there.
Glass.
You can't have light traveling through a non-transparent material, and you know.
You could have water and glass.
Yeah, whatever. It doesn't matter. Okie dokie. So, Zach, did you write something for part A, or do you have a sentence or anything for part A?
No, just.
You drew the diagram.
Just drew the-
Yeah. Did anyone write anything for part A yet? Dorian, did you write something for part A?
Angle.
Okay, well let's just hear what you wrote. Go on.
Angle from
Incident.
Okay.
in
This-
which
this-
light travels between. It's kind of bad. So it's fine.
Did anyone else write a sentence?
Critical angle is the angle between the incident.
Okay.
Mostly, like when light
And-
travels between two different mediums, it is refracted along the surface.
Yeah. Yeah. These aren't great sentences. Let's see. They just want the critical angle, so you don't need to talk too much about other things, okay? So the critical angle is the incident angle in the first material, the first medium, that would cause a 90 degrees refraction in the second material. Something like that, you know? But guys, I don't want you thinking that this is the only sentence you can make to explain this, you know?
90 degrees.
What did you write so far?
It is the angle, the incident angle that would cause a 90 degrees.
Yeah, go on. Go on, tell me.
90 degrees
Angle.
Diffraction.
Refraction angle
Angle.
in
The second medium.
the second medium. Yeah.
Can we say stuff
And it's
like
the angle between the normal and the.
Yeah, but you don't even have to say that, because the moment you use the word incident angle, it means
The angle between.
the angle with the normal. And when you use a 90 degrees refraction, again, the word refraction implies measured with the normal, because this is part of the meaning of the word. There's no need for you to say it, you know. However, if you say theta 1 and theta 2, well, then that's different, because there's no meaning to theta 1 and theta 2 that means with the normal. But the word incident and the word refraction, that means with the normal.
Can we say stuff like, say is the incidence angle right before total internal diffraction occurs?
You could say, if you wanted to say something like that, you could say the critical angle is the minimum incident angle to cause total internal refraction. That would work.
But is it always total? Because as we saw in the other problem, they
Yeah, no, that's fine. No, that's fine to have the word total in there, because I have the word minimum. Yeah, no, that's fine. Okay, and the second part is easy. What's the critical angle here for the diamond? Assuming it's diamond air. So it's
Sine 1 over 24.
yeah, sine inverse 1 over 2.4.
But when it says it travels from the diamond into the air.
No, we don't have to think here. We don't have to think, because there's only Dorian, there's only one possibility that's mathematically correct. We can't do it the other way around. Yeah, we can't. We can't. So there's never any ambiguity with the critical angle. You never have a
It
choice.
does say for the light coming out of the diamond into the air.
Yeah. So what happens is the light enters the diamond, and now you're looking at the light that is in the diamond exiting into the air.
So that
So the light going in has no critical angle, because we're going from a low to a high index. So you can never choose a critical angle from air to diamond that would cause it to come back to the air. However, when the light is in the diamond and leaving it to go into the air, there is a critical angle that could cause it to actually internally remain. So what would you think is the effect of having light remain inside the diamond?
that's what I was going to ask you.
Yeah, what's the effect of that? If some of the...
So that would mean
well,
that
well, firstly, what's the critical angle you got there? What's the critical angle?
24.6.
Now that's a low angle, relatively speaking, right? So, my question is, based off of probabilities, roughly speaking, how much of the time will the light be more than 24 degrees? A lot of the time, or a little bit of the time? Assuming every angle is equally possible. Most of the time. Therefore, most of the time the light gets internally refracted. So most of the time the light is re-entering the diamond. And it's probably after it's fourth attempt does it actually exit. So what would that cause the diamond to do? If sparkle, exactly, because the light is almost like you quadruple the light, because the light gets trapped, it bounces around a couple of times before it can exit, because it needs to get an angle of less than 25 degrees to exit, because as soon as it's more than 25 degrees or whatever number you said, it'll internally refract, hence the sparkle. Yeah, and I think diamond actually is a material with a very high refractive index, which causes it to have a very low critical angle, which causes the light to be easily trapped inside for a couple of bounces. Yeah, make sense? Yeah. Next now, I will do this one, and then I'll let you try number 5. A ray of light is instant on a glass block, and I'm assuming it's coming from the air. Maybe not, yes. An angle 20. So that's 20 degrees. The air has an index of 1, and the glass has an index of 1.43. And then what happens is it refracts. So we get an angle here. I'll just call it theta. Determine the speed of light in the glass block. Well, that's using the formula I gave you. N equals V over C, isn't it? Or was it C over V? That was C over V.
Number of moles equals concentration over?
No, now you're confusing me. No, maybe it's the other way. Hang on. C over V, because V will always be less than C, and this needs to be more than 1. Yeah, that's it. So, yeah, 1.43 equals, I think it's actually 2.99 times 10 to the 8, really. I'd have to check the formula book, whatever it is. Well, I'll just be lazy. 3. 10 to the 8 over V, and we want the V. Okay, so the V will equal 3 times 10 to the 8 over 1.43, which will be what? 2.
2.1, 2, 3, 4, 5, 6, 7, 8.
Well, what's after the 2 point?
2.097, so 2.0110
10.
times 10 to the 8 meters per second.
Okay, are we okay with that, folks? Yep. B. What is the angle? That's the theta here. So let's see that you don't screw this up. Sine. What?
Theta 1.
Yeah, so in this case?
1. No.
20, thank you. Over sine theta.
Equals
N2. So 1.
n is
4 over
1.
Good. So that means theta will equal sine inverse sine 20 over 1.43. Okay. And finally C. What is the critical angle? Boring. Sine inverse 1 over 1.43.
44.4.
All the 4s.
Does it get much more difficult than this?
Yeah.
Yeah.
But most
You
of the
said
time,
older questions.
the very old ones. But I don't think you have to worry too much about that, because I have no reason to believe that they'll revert to the older questions. Because these ones we've been doing, what years are they dated from? 17, 18, 07, 08, 16, 17, 17, 18. Yeah. Okay, 5 is a good one because it's a little bit different because I don't think they're looking for the theta, they're looking for the wavelength. So do you remember that I gave you other versions of Snell's law? I think you might need one of those here. Do you need to write that down or do you have it? You have it? One sec, okay. Yeah, okay. So give 5 a go there. Let me just scroll down a bit. Right, give 5 a go. Sodium light is just the name of the light source. It's like a sodium lamp, I think. I don't know what.
It have a specific wavelength.
Yeah, a particular color. In fact, maybe it's a yellowy color. I'm not sure. I have a feeling that the reason the author wrote in sodium light is because that maybe is the light that's used in the definition of refractive index.
So, yeah, it would have to be yellow light.
Yeah.
Any other color we could.
Yeah. Oh, but I'm saying in the experiments for measuring refractive index,
Yeah.
I think
It's
sodium light is the one that's used.
Oh,
Yeah.
okay.
Because it doesn't really matter what color light you use in the definition, as long as you consistently use one particular color to define the refractive index for materials. You know. Anyways, a diamond's placed in a tank of water. What is the critical angle for the light when it reaches the boundary between the diamond and the water? Well, this will only take you a few seconds to do. For which part, Zach?
Second one.
Theta 1, theta 2, lambda 1, lambda 2.
Oh yeah. So sine. Which goes on top?
It's no choice. Mathematically, it can only be one of them.
No, but not for. It's for the second part.
Ah, it's sodium light in the diamond. In the diamond.
No, it's A. Now it's an A.
No, for part 2.
Yeah.
No. What's happened is
Oh, okay. No.
the sodium lamp has shone some light onto the diamond, so the wavelength as the light went from the air to the diamond has changed due to the refraction. Guys, in number 2, if you're confused, it's air to diamond.
Yeah.
It's quite difficult to put a sodium lamp inside a diamond.
Expensive.
Nanotechnology might be required, or a really big diamond.
What would it affect it? Because in the first one it was from the water.
But you can't use the same refractive field.
Because it's
You're right. Question. Oh, sorry. I apologize. I believe I'm misreading the story here. The diamond is inside a tank of water.
Yeah.
Well, firstly, that's strange. Yeah, I'm sorry. I'm very sorry. What's happened in part 2 is just it's part 1 still. You worked out.
The angle, the critical angle between the diamond and the water.
Oh, do you know what? It has nothing to do with Snell's law. It's not a refraction problem at all. I'm sorry. It's an N equals C over V formula. That's what it is. For some reason I was thinking it was a refraction, but there's no mention of angles anywhere in this story. So there's no Snell's law in this. It's just n equals c over v. I better do this one. The first part, I hope you got it okay. Critical angle equals sine inverse 1.33 over 2.417. And what do you get for that? 33.4. Okay. Now, for part 2, n equals c over v. But, well, actually, maybe I want to, yeah. Okay. Do you know what I'll do? I'll get the v first. V equals c over n. Now, what are we looking at? What's the n? Sorry, it's in the diamond. 2.417. So, can someone tell me what this is, please?
1.24 times 10 to the 8. And from that you get the wavelength.
Yeah. Now, I need you to tell me, this is where you have to be careful. Can you look up for a moment, folks? So that V there, that's how fast the light is moving in the diamond. Right? So is it moving at speed c? No, it's moving at this slower speed. Okay? You can use the wave equation. Do you remember V equals lambda f? Do we know V? We do. We have it right there. We want lambda, so all that we need to know is f. Now, f is the same as what?
Okay,
Yeah?
give us lambda for air. For air.
Yeah, we're going to work that in now. Okay? Now, this lambda is the wavelength while it's in the diamond. I'll just write D here for diamond. And the V, that's the speed of the light when it's in the diamond. And the frequency, that is when it's in the diamond. However, I think Dorian, you remember this from the last class. What's interesting about frequency? It doesn't change, does it? So that frequency of the light in the diamond is the same as when it's in the air. And if I use the formula V equals lambda f, so F equals,
So 3 times
C equals lambda f, so F equals C over lambda
So 3 times 10 to the 8 over that wavelength.
in air. So sorry, I'm nearly there. So that's V in the diamond, lambda in the air, over the speed of light in the air. So this number times 589.3 times 10 to the minus 9 over 3 times 10 to the 8. Well, that and that cancels. So it's just going to be 1.24 times 589.3 over 3 nanometers. 244 point.
It's times 10 to the minus 7.
Yeah. So if we turn it into nanometers, I'm sure it'll be like this.
Yeah.
Yeah, that makes sense because that over that is roughly a half.
244, yeah.
Hard. That was kind of a hard one. Now, what's happened to the wavelength? Has it gone up or has it gone down as it moved from air to diamond? Yeah, so the wavelength has moved down, right? What's happened to the refractive index? Did it go up or down when it went from air to diamond? It went up. So, this formula is not in the notes. It's not in the slides. It's not in the physics book. But I'm willing to bet that there's a formula that says lambda 1 over lambda 2 equals n1 over n2. I mean, I'm pretty certain that this is going to work because I can really tell that the relationship, it's a ratio. Yeah. So, I wonder if we use this, would we get the exact same answer? I think so. Lambda 2 would equal n2 over n1 times lambda 1. Yeah? Which is, what was n2 please, the diamond?
2.47
over r
over 1 times lambda 2.
Oh, I'm sorry, I wrote this upside down. I meant to put here n2, n1. It had an opposite relationship. So n2 equals lambda 1 over lambda 2 n1. That's a 1, that's a 2. Okay, what was lambda 1? It was 589.3 times 10 to the minus 9. What was n1? It was 1. Good grief, Stephen. Sorry, hang on guys, sorry. I'm a bit brain dead right now. Just give me a moment, please. I'm looking for lambda 2.
Yeah.
Lambda 2 equals n1 over n2 lambda 1. Okay, we're good. 1 over 2 point, what was it?
417.
417. And then the lambda 1 was 59. Okay. Now give me the good news. Tell me that works out to be 244.
Yeah, it does.
Nice.
243.81.
Yeah. So I didn't give you this rule. It wasn't anywhere. But you can kind of easily show it from Snell's laws. Because, do you remember Snell said sine theta 1 over sine theta 2 equals n2 over n1. And Snell also said sine theta 1 over sine theta 2 equals lambda 1 over lambda 2. So you can put these together and you can get a relationship n2 over n1 equals lambda 1 over lambda 2. Okay, so we're starting to get into the harder ones now. I wonder if the solution is here. I wonder which way they did it. What do you think, the first or the second way? I maybe think they might have gone with the second way. Oh no, they went with the first way. Yeah, 244 nanometers. Okay. Well, I guess I shouldn't be surprised because, like I said,
at the bottom it says
or. Oh, nice, nice. Oh, I like it when it all comes together like this. It looks like I planned it. Okay. Right, is that okay? Yeah. Let's have a look-see now at the next one. Okay. This one is extremely similar. Again, it's two materials. Right, see what you can do with this one. So the first one's definitely a Snell's law. Okay, you got that? Have you got that, folks? Got it, Gina? Yeah. So let's have a look. Okay. So I have sine theta over sine 42. Is that it? No, 1.33 over 1, isn't it?
Yeah.
Good. Did you all get that? Yeah, so what's the theta?
Sine inverse.
Sine inverse, yeah, 1.33 sine 42. So what do you get? 62.9. Okay. And what's the wavelength? So you can say sine 62.9 over sine 42, or you could say 1.33 over 1. That's equal to lambda 1 over lambda 2. Now, it doesn't really matter. These will be the same thing, so I'll just go with this, okay?
And you just need
We want it in the water, so
V over F.
we can say, yeah, lambda 2 equals lambda 1 over 1.33.
V over F.
Yeah, C over F over 1.33. Yeah, okay. So that's 3 times 10 to the 8 over 5.43 times 10 to the 14, all over 1.33. Did you get that, Gina? Yeah, what did you get for lambda 2?
4.15.
Oh, you have it 4.15?
450 nanometers.
You got this? Yeah? Yeah, okay. Nanometers, yeah, okay.
The same.
Wait, did you say 4.11?
4.15.
15, okay. Yeah, it's okay. Yeah. Yeah. Oh, yeah. Yeah? Yeah? Continue?
Well, that lambda actually makes it really easy. Lambda 1 over lambda 2.
Yeah? Yeah.
Let's try it.
A semicircular block of glass is immersed in a clear liquid. This liquid has an index of 1.25 and the glass is 1.52. Determine the speed of light in the glass. Right, calculate that for me and tell me what you get for part 1 here. He's possessed, man.
Oh no.
Okay, what's the speed, please? It should be what, about 1.48 or something, is it? Times 10 to the 8th. Guys, what's the speed for the first part? Now don't look around, Diego. You can calculate this. It's not a difficult one. Hello? Anybody home? What's the speed for the first part?
Is it V1 or is it V2?
Oh my goodness. The formula. What is the speed of light in the glass?
3 times 10 to the times.
Okay.
Three
3 times 10 to the 8.
Okay. But does it get slower and slower, or do we not consider?
That is a very interesting question, and I was just thinking that as you asked me. I think I'll have a look at it. Let's have a look at it, actually. I'm sorry. I thought you guys were just being a bit slow, but now that I think about it, the question isn't as easy as it first seemed. So, you have your light in the air, yeah? Then you have it in the glass. Is it? No. In the...
Water.
Well, it's a liquid, whatever it is. And then finally, what's the last material? It's glass. Now, what's the refractive indices here? The first one? 1. And here?
1.25.
And then here?
1.52.
1.52. Yeah. So here, this one is a bit like the N1 and this one's a bit like the N2. Okay? And here, the velocity, what's the speed of the light in the air? That's c. Okay? So if I use my formula from earlier, you could say V1 over, and here we'll call it V2. V1 over V2 equals N1 over N2. Yeah? So then V2, will it be bigger or smaller? Of course it will be bigger, according to this. So I've done something wrong, haven't I? Oh, I have my ends upside down, don't I? Classic Stephen mistake. V1 over V2 equals N2 over N1. Yeah, Stephen. Right, so V2 equals C over 1.25. No, don't type it in just yet, please. I'll just leave it as 4/5 C. That's what that is. Isn't it? Yeah, it is. Isn't it?
5 over 4.
Yeah, it is. No. Now, here, look. I'll call this one, guys, look. Diego, put it down. This one N3. Okay, so 5 over 4C over, and this is the thing we're looking for, V3. V3 equals N3 over 1.25. Okay, interesting. So that's 4 over 5C times 1.25 over 1.52 equals V3. So Dorian, your question, which we were both thinking, is it doesn't seem to matter because in the end this one cancels with this one and you get V3 equals C over 1.52. But I could have used the formula at the beginning, N equals C over V. It does work. So you were asking me, does it matter that the light was going slower before it came into the glass?
Yeah.
And the answer seems to be no, it doesn't matter. We just calculated it. Apparently, but the maths don't lie, man. The maths don't lie.
So it slows down and speeds up again.
No, I guess because it's...
Go figure.
No, because refractive index is not from liquid to glass, it's from air to glass. And so it's
Yeah,
more like this.
I guess that's one way to think about it.
Maybe.
He doesn't.
That's okay. That's okay, Diego. The moral of the story is we could have used the formula N equals C over V at the beginning.
You don't have to console it.
So V
It
equals
goes from
C
straight
over
from
N.
air to-
Exactly. We can pretend it went straight from the air to the glass. 3 times 10 to the 8 over, what was the refractive index of the glass?
1.52.
Okay, so what answer do you get here?
1.97 times 10 to the power of 8.
I feel like, Dorian, that wouldn't be a useful tidbit of information to remember in the future. That we can, when calculating the speed in a material, it's not important what the previous material was that the light came from, it would seem. I think we just have to accept that as a fact.
My brain can't compute it.
Unless
Doesn't
Yeah.
see
But light behaves very differently,
Yeah.
okay? Because first of all, it doesn't need a medium. It travels at constant speed. You know, light's behavior is very strange. It's not like, I know what you're picturing. You're picturing like a car was slowed down in one medium
Yeah.
and then it enters another medium. And obviously the previous speed was important.
There's no mass.
But it's not-
Yeah.
It's not the case for light.
No, it's because the refractive index.
You think because it's from A to in
Because
air
the
glass.
refractive
So
index
if you
is-
did the
is compared
refract-
from
yeah.
the
But
from
what
air.
if you compared the glass to the liquid then?
If they give a refractive index from there, if they don't give the refractive index, they only give like the speed before, then it matters. But if they already gave you the index, then it was always 2.
What were you asking from, what? Glass to,
Glass to
If
the
it were-
liquid.
Yeah, then
and
it
you want the
matters.
speed in the liquid? Then you just need to know the refractive index of the liquid. You don't need to know anything about the glass.
Unless they give you something like the angle, and then they don't give you the refractive index.
Yeah, they might force you to do a calculation of some kind, but no. And the last part here is, what are they looking for here? They're looking for the critical angle. Yeah?
1.5.
So it's going to be sine inverse 1.25 over 1.52, isn't it?
Yeah. 55.3.
You okay with that? Yeah. Now, just before you go, there's something I want to show you, because we were talking earlier about the strange behavior of light. So I'll just give you a bit of an example here. So imagine here we have a straight road, and here's a car going at, let's say, 10 meters per second, and here you are standing at rest. And maybe you have some kind of speed gun to measure the car's speed. So when you look at this car, you say, okay, to me, it looks like the car is going at 10 meters per second. Fine, okay. Now, instead, let's imagine you have the car here. It's going at 10 meters per second. And then you're in a car, and it's going at, let's say, 1 meter per second. And you... here's the speed gun. Here's the speed gun, for example. As you look at this car, will you say it's going at 10 meters per second? What do you think?
No.
No. What would you report its speed as?
9.
9. Yeah. Why?
Because
You're going 1. So relative to you, it looks like it's only going at 9. And in fact, if you were going at 10,
It would seem like
it would seem like it's stationary,
yeah.
through your point of view. Now, let's just, so keep that in your mind. Let's just change it a little bit. Here, you're standing here, and you see a light wave, and you report its speed as c, whatever c is, 3 times 10 to the 8. Okay, and then you're here, and you're moving this way with v, and you see the light wave, and then you have a friend, and they're here, and they're moving the other way with v. Okay, so would you say would you say this person would say the speed of the light is c? No, what would it be? C minus v. And what would this person say? C plus v. Very good.
But you can't go faster than the speed.
No. You're still just going at v. You're just reporting the speed that you see. You see the light going at c minus v, and here you see the light going at c plus v. What Einstein discovered was that both people would still see the light moving at c, even if they're moving in opposite directions. Okay? So this means no matter what direction you're moving, no matter what speed you're moving at, you will always see the speed of light moving at the speed of light, even if you're moving in an opposite direction to it.
Is it because the speed of light is so big that...
No, it's a feature of the universe. That light, not only is light constant, but it's constant for everyone moving in any direction at any speed. Yeah. It's very strange, isn't it? It's very strange. Like, if Lynn was moving towards me, and I was moving backwards, then I should see him moving towards me at a slower speed because I'm moving away from him.
The same as when you're on a train.
Exactly what you're saying on a train, yeah.
You see, like
Yeah.
a window.
But if Lynn was a light wave, I would still see him moving at c, even if I'm trying to move away from him. And this is what Einstein figured out.
Is it the same for sound? Or?
No, it's only for light. It's only for light. Has anyone ever seen this before?
I know the experiment with the lightning.
Yeah. So this is Einstein's theory of relativity. You know.
He was
Why
talking
does that
about
happen?
people in trains or something.
Yes, he used trains as an example.
And
So
the
like,
lightning strike.
if you're standing on a train and you see a light wave moving along the track beside you, will it look like it's moving slower because you're moving on a train parallel with it? And the answer is no. And the reason for that is because what's happening is as you move at this speed v, your clock is moving slower. Time passes more slowly. So this is what makes the light.
You don't even see things in real time. It still takes time for the window.
And it also the yeah.
On our retina to be pretty.
Well,
But it's more,
Yeah.
even if you were using scientific equipment, you know, what's happening is your clock is ticking slower. That's what makes the light look like it's going at the same speed. Anyways, that's if anybody was going to do. If anybody, do you have a presentation to do in semester 2?
Yeah.
Yeah, I remember a couple of years ago somebody did a presentation on this topic. It's a very interesting topic. So if you were thinking of something interesting to do on your presentation, you could pick this topic, the speed of light. Yeah? All right. Will you please finish these for homework? You have 8, 9, 10, 11, 12, 13,
18 or
14, 15, 16, 17, 18. Oh, japers. Okay. Do you have class tomorrow with me?
Yes.
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 The first 2 classes from 10.
Will you be able to get those finished for tomorrow or not? So what else do you have to do?
Chemistry.
No,
Oh. Can you do at least 3 and then maybe finish them on the weekend?
Yeah.
Yeah.
Yeah? Okay. All right. Right.
Oh, no, I have to run.
You have to what?
Run